Well, hello, you Math 2 Enhanced students. It's been a while since we've been together, and so I thought it would be important to start off our digital long distance learning by going back over the last lesson that we ended on before we got school canceled on us. So let's kind of recap the lesson on radical functions. Remember, this unit is dealing with inverse functions. What is an inverse and how to tell if a function's an inverse. And as a result of that, we have this thing called a radical function, and it is a result of the inverse of a parabola. So with that said, our goal is to be able to graph a radical function today, specifically a square root function. Okay, with that said, let's see if we can remember a few things. First of all, let's say that f of x is equal to x minus 3 squared minus 4. Well, before we go any further, let's understand what f of x is. F of x is a parabola because the exponent is squared, and it has a shift to it of 3 units to the right, because remember we changed the signs on that, and 4 units down because we hold that sign. So 3 units right and 4 units down. We have a parabola that opens up because our a value is positive, and it has a normal slope pattern of 1, 3, 5 because the a value is 1. Now, going on, it says that f is invertible. F is an invertible function. Well, what does invertible mean? Invertible means that it's 1 to 1. Invertible means that if you take its inverse will be a function. And if you remember how to check for invertibility, you test first the vertical line test to test to see if the function is, or to see if the equation is actually a function, and then you test the horizontal line test to see if it's invertible. If the horizontal line test passes, then that means its inverse is going to be a function as well. Well, if we think about a parabola is a function because the vertical line test passes the vertical line test, but it is not invertible because the horizontal line test fails. Because if you think of a parabola opening up, if you try and draw horizontal lines, it's going to hit that parabola in 2 different places. So what we're saying here is that this function is invertible, which means we have to restrict its domain so that it's invertible. In other words, we have to cut off half of the parabola so that it is 1 to 1. And so when we go to cut off the parabola, we are altering its domain so that when we go to look at its inverse will be a function, because we know the inverse of a full parabola is just a sideways parabola, and that's not a function. So remember how we cut up a parabola. We cut up a parabola at its axis of symmetry. So we can either look at the left-hand side of the parabola or the right-hand side of the parabola. And because the axis of symmetry is x equals 3, because the vertex was 3, negative 4, we can either restrict the domain to be negative infinity to 3 or 3 to infinity. It just depends on which part of the parabola we want. Either way will work. Now, the next question is, what is g of x? G of x, notice, is the inverse of f. G is the inverse of f. So if you think about how to find an inverse function, the first step is to replace the x and the y, or swap out the x and the y. So instead of saying y equals x minus 3 squared minus 4, we're going to say x equals y minus 3. Oh, let me take a step back. We're going to say x equals y minus 3 squared minus 4, and then we're going to solve for the y value here. So we would add 4 to both sides, so we get x plus 4, and then we would square root both sides, and then we would add 3. And so as a result of that, we'd either get y equals the negative radical x plus 4 and then plus 3, or we would get y equals radical x plus 4 plus 3. And the reason we're going to get one or the other is because, remember, this is going to be the bottom half of the parabola, the sideways parabola, and this is going to be the top half of the sideways parabola. We'll get more into that later. So for part C, it says graph f of x and g of x on the same graph. Well, I'm gonna graph both cases. I'm gonna graph the case where the domain is from negative infinity to 3, and I'm gonna graph the case where the domain is from 3 to infinity. So in the first one, here's the entire parabola. That's the parabola with a vertex of 3 comma negative 4. And we can see it perfectly. We got the slope pattern going on. We got the correct vertex. It's opening up and everything. Now, if I look at just the left-hand part of that parabola, in other words, if I look at the domain from negative infinity to 3, this is what that parabola looks like. Now, when I go to graph the inverse of it, remember the inverse is when you take a coordinate and you flop it. So instead of this coordinate, let's see, this coordinate is 3 comma negative 4. We're gonna flip those values, and so our new coordinate is going to be negative 4 comma 3. So that's going to be the vertex, and then we can pick a few other points if we want. Let's look at the y-intercept here. This coordinate is 0 comma 5, so therefore the coordinate on the inverse would be 5 comma 0 here. But ultimately, if you plot all those inverse points, you would end up with half of the parabola, in fact the bottom half of the parabola, and you can see that here because you have the negative out front. Now let's take a look at the other half of the original parabola. So if we erased everything to the left of x equals 3 and just focused on the domain from 3 to infinity, we would get this part of the parabola, okay, this half. And then if we plot the inverse of that, again, this coordinate here is 3, negative 4. So our new coordinate would be negative 4 comma 3. So you'll see it's the same vertex point as this one. But then if we look at, let's say, the x-intercept, this is 5 comma 0. So our new point's going to be 0 comma 5. If we do that to all the available points, we're going to get the top half of this parabola. So if you can put the green together with the blue, you would get your full sideways parabola here. But we didn't want that because that's not a function. So we restrict the domains so that it is a function. And notice, just going back to a quick review, if you look at the domain of the original function from 3 to infinity, that is the same as the range of our inverse function. So notice the lowest part of the inverse function is 3 and it goes up to infinity. And then in this case, if we look at the domain of that case from negative infinity to 3, well then the range of the inverse is going to be from negative infinity all the way up to 3. And so we can see graphically how they're related, and we can start understanding how this equation is creating this half parabola, sideways parabola. The other thing to remember is graphically, to find an inverse or to check to see if two functions are inverses of each other, you would see a reflection about the line y equals x. And we can see that if I draw a line y equals x here, we can see that the purple, if I reflect the purple curve over that line, we would get the blue curve in fact. All right, so that's just a recap, a big recap of inverse functions in general, about the relationships and things like that. Let's go ahead and take a look at the next slide here. Here we have the parent functions of three different functions. We have y equals x squared, y equals rad x, and y equals negative rad x. Well, we can graph the first one pretty easily. It's just y equals x squared. So the vertex is 0, 0. Slope pattern's 1, 3, 5. It opens up. That's perfect. This next one is radical x. And we know that that's going to be the inverse of this parabola because if I flop the x and the y's, I would get x equals y squared. And then I square root both sides, so I get y equals radical x ultimately here. Now, here is the top half of the parabola, and here is the bottom half of that sideways parabola. The vertex would still be 0, 0, and in this case we're opening up, and in this case we're opening down. And so notice the slope pattern here. I know it might be hard to see here, but in the green we went up 1 over 1, and then from that point we went up 3 over 1, and then up 5 over 1. Well, if I'm following the same pattern, or the same idea here, Instead of going up 1, well, I am going up 1 over 1, but then I'm going up 1 over 3, and then up 1 over 5. And so you can see that you have an inverse relationship here, because remember, if you talk about linear functions, the slope of an inverse function to a linear function is just the reciprocal. So if you look at the slope of a line, and let's say the slope of the line is 2/5, that means its inverse is going to have a slope of 5/2. Well, it's the same here. If this slope pattern here says to go up 5 over 1, then in the sideways parabola, I'm going to go up 1 and over 5. Okay, that's just something that we're going to get more into later. But here's something else I wanted to add to this. Notice, let's see here, where is it at? Oh, there it is. I put those points in so we can see it. We can see that from here to here, I went up 1 over 1, up 3 over 1, up 5 over 1. Here, I went up 1 over 1, up 1 over 3, up 1 over 5. So it was the inverse of it. And then same thing here, but instead of going up 1, I went down 1, right 1, down 3, or down 1, right 3, down 1, right 5, because I was looking at the inverse of the back side of this parabola. All right, looking at the parent functions, and if you remember the shifts, the vertex form specifically of a parabola, the h value represented the horizontal shift, and the k value represented the vertical shift. And so if we have this equation that says y equals x minus h squared plus k, then we can see the vertex is actually h comma k, because we shift over h units to the left or right, and then k units up or down. Well, that holds true for a radical function as well. If you have x minus h inside the radical and then plus k outside, that's the same kind of shift as you had in the parabola. You're going to go h units to the left or right, and you're going to go k units up or down. What I notice here is the thing inside, we call this the argument, the thing inside x minus h, or sorry, the operation is the argument, I believe, but the thing inside the operation here is x minus h. What are we doing to x minus h? We're squaring it. In this case, what are we doing to x minus h? We're square rooting it. And then after we square here, we're adding k. Well, after we square root here, we're adding k. And so the pattern is the same. We're shifting the same amount. It's just what kind of pattern do we get? Do we get a parabolic shape, or do we get a radical shape? And it's going to be the same thing for the bottom side of that sideways parabola. We can see a shift of h comma k, and it's just going to be the bottom half, because that's negative, of a sideways parabola. All right, let's take a look at this next slide here, give you an example of what this looks like. I've got f of x equals negative radical x plus 5 plus 2. Well, the first thing I see is that I have a negative here. That means I'm going to have the bottom half of my sideways parabola, because this is a radical function. The next thing I notice is that I have plus 5 inside the radical. So that's going to shift the parabola 5 units to the left, because remember, we changed that sign there. And then I'm going to shift my parabola, or my sideways parabola, 2 units up. All right. So there's that. We can graph that. Take a look at this graph here. We can see it pretty easily. We shifted 5 units to the left and 2 units up. There's my vertex. We are looking at the bottom side of this sideways parabola because of the negative. And then notice my slope pattern. My slope pattern is down 1 over 1, down 1 over 3, down 1 over 5, and so on. So instead of going up 1 over 1, up 3 over 1, up 5 over 1, we're going up 1 each time, or down 1 each time, and then over 3, over 5, over 7. Okay, that's fine. We can see that slope pattern just fine. Let's go ahead and do a practice problem here. So I would go ahead and pause this video and graph this function, and then when you're done doing this, push play and then watch the rest of this video here. Okay, so for g of x is equal to x plus 1 squared minus 3. So that's going to be an easy parabola to graph. It shifted 1 unit to the left and 3 units down. The a value is 1, so that's an easy graph. Notice it's giving us a domain restriction of negative 1, less than or equal to x less than 2. H and g are inverse functions. Graph h. Well, we have a couple different ways of doing this. My goal is to be able to do this analytically and then solve the result. So to do this analytically, to find an inverse function, I need to swap the x's and the y's. Remember, g of x is just another way of saying y. So I'm going to replace that with x, and I'm going to replace x with y. So it'll say x equals y plus 1 squared minus 3. And then our goal from here is to get y by itself. So we're going to first add 3 to both sides. And then we're going to square root both sides. Remember, when we square root, we really want to put a plus or minus out front here because we were the ones doing it. So I didn't do that there, but I should have. And then I'm going to subtract 1. And the reason I'm going to put the plus or minus out here, because now I can look at this function, am I talking about the top half of this parabola or the bottom half of this parabola? I don't know yet, because I'm given this domain restriction. I've got to be able to visualize this and understand this a little bit. So what I'm going to do is I'm going to graph this sideways parabola. I notice that I have a vertex that shifted 3 units to the left and 1 unit down. Okay, so let me take a step back real fast. So since y equals radical x plus 3 minus 1, we're going to call this function h of x, because that's what the inverse was named. And h of x equals rad x plus 3 minus 1. And notice this. This says negative 1 is less than or equal to h of x is less than 2. Because remember, the domain of our original function is going to be the range of our inverse function. So we replace the x value with y, because that's what inverses do. They replace the x's and the y's. Since this says x, we're going to put a y there instead. And notice I just called it h of x. So we know that the range is from negative 1 to 2. Now watch what happens to this graph. We don't know yet if it's plus or minus. Well, let's go ahead and graph this parabola and see. We're going to shift 3 units to the left and 1 unit down. Okay, so we can see that vertex there. From here, we see that the slope pattern is going to be, well, the inverse of 135. So we're going to go up 1 over 1, up 1 over 3, up 1 over 5 for the top part. And we're going to go down 1 over 1, down 1 over 3, down 1 over 5 for the bottom part. And so we get this full sideways parabola. But then this isn't a function, so we have to erase part of it to be able to see where our function lies. Well, that's where our range comes in. Because the domain, again, because the domain of g was negative 1 to 2, that means the range of h is negative 1 to 2. So remember, a range is the y value. So what I'm going to do is I'm going to draw 2 horizontal lines, one at y equals negative 1 and one at y equals 2. And we know that our parabola has to be in between these 2 dotted lines. And so we can see everything outside those dotted lines, the stuff below and then that little piece above, have to be erased. Okay? So we see that's erased, we see that's erased, and therefore we now understand that the reason, the fact that we have the range being from negative 1 to 2, that we are seeing the top half of that parabola, and therefore we are looking for the positive out front, not the negative. Okay, so with that said, we can get rid of those dotted lines and we can see our graph with its domain restriction or its range restriction. And because the range restriction is from negative 1 to 2, our domain restriction would be from negative 3 to 6 here. Okay, with that said, based on the range of the function, we know it's going to be the positive value. All right, let's go ahead and take a look at what the a value does. We talked about that briefly a minute ago, but let's talk about it again real fast. It says, looking at a function y equals ax squared versus y equals a rad x. You see, if I were to plug a number into x and then solve for y, the first thing I would do is square that number, and then I would multiply by a. Well, the first thing I would do here is square root that number and then multiply by a. So ultimately, this a thing is kind of doing the same thing. Remember, the a value in a quadratic is a vertical stretch or a vertical shrink. If a is greater than 1, it's going to be a vertical stretch. And if a is between 0 and 1, it's going to be a vertical shrink. Well, it's going to be the same thing for a radical function. Okay, so let's take a look at this. If I'm looking at f of x equals 3 rad x, well, this one's easy. There's no shift to it. So graphing that, first of all, we can see there's no shift. The second thing is that we have a vertical stretch by a factor of 3 because the a value is 3. Well, do you remember how to determine a vertical stretch or how to use the vertical stretch to graph a function? It wasn't that difficult. We just took our original slope pattern and multiplied it by the a value, and then we followed that new slope pattern. So in our case, we know that the slope pattern for radical x is 1 over 1, 1 over 3, and 1 over 5. In other words, up 1 over 1, up 1 over 3, and up 1 over 5. That was our original slope pattern because these are all the reciprocals. They're all the flipped slopes of our original parabola, right? If we flip these over, we got 1, 1, 3 over 1, 5 over 1. That's from the parabola. Because this is the inverse, we're going to flip those average slopes. Now, what we're going to do with those average slopes is we're going to multiply it. We're going to multiply it by 3 because we have a vertical stretch of 3, or by a factor of 3. So here when I multiply by 3, I end up with 3 over 1, 3 over 3, and 3 over 5. And so when I go to graph these two, just to compare the two, rad x is pretty straightforward. Notice the points. Notice the points, the vertex, 0, 0, then up 1 over 1, up 1 over 3, up 1 over 5. For our function that says 3 rad x, we're going to start at 0, 0, and then we're going to go up 3 over 1, up 3 over 3, and then up 3 over 5. And we can see our new points there. And so you can see the vertical stretch. Okay. Notice we didn't go any further over for each point. We still went over 1 each time, but well, not over 1 each time, but over 1 over 3 over 5. But our vertical shift changed. Our vertical stretch changed. All right, let's go ahead and take a look at a couple practice problems here. Give these two a shot. Part A should be pretty easy. Part B is going to have a little bit of a, you got to be careful on this one. And once you're done graphing these, come back, push play, and pay very close attention to part B. All right, for part A, I notice that I have a shift of 4 units to the right and 1 unit up. So I'm going to go ahead and plot that point, 4, 1. And then from there, I know that I'm looking at the bottom half of the parabola because the a value is negative. And I know that I have a vertical stretch by a factor of 2. So I'm going to take my original slope pattern of 1 over 1, 1 over 3, and 1 over 5, and I'm going to multiply that by negative 2. So I end up with negative 2 over 1, negative 2 over 5, sorry, negative 2 over 3, and negative 2 over 5. So that means I'm going to go, down 2 over 1, right? Then I'm going to go, where am I? Down 2 over 1, down 2 over 3, and then down 2 over 5. So I can plot those points. Down 2 over 1, down 2 over 3, and then down 2 over 5. And there's my graph for part A. For part B, it seems pretty easy. What is the h value? The h value is 0, so that means we're not shifting it to the left or the right, but we're shifting it 6 units down, so that's where our vertex is going to be. We do know that it opens up because the a value is positive. But now here's where it gets a little tricky, and you have to be careful here, okay? We are going to take our original slope pattern of 1 over 1, 1 over 3, 1 over 5, and we're going to multiply it by a half. Now when we do this, we do not want to change the denominator, okay? We just want the numerator to change. So it's not that we are multiplying 1 times 1 and 2 times 1. We are technically, what we're doing here is we're multiplying the original slope pattern by 1 over 2 over 1. That's probably the best way to look at that, okay? That way you're not changing the denominator, you're only changing the numerator. So what is 1/2 times 1? Well, that's 1/2. And then over 1, so we say 0.5 over 1. And then 1/2 times 1 again is 0.5. 1 times 3 is 3. And then 1/2 times 1 is 0.5, and 1 times 5 is 5. And so what this is telling us to do, it's telling us to move up 1/2 and go over 1. It's not telling us to go up 1 over 2. We still only want to move the same amount each time. 1, 3, 5. 1, 3, 5, 7. Every time, that's how much we move over for each movement. It's the vertical change that we need to change each time. So we're going to go up a half over 1, up a half over 3, and up a half over 5. And so we get these points here. Very important that we pay attention to that concept here. And then connect the dots, and we got our parabola. All right, so that wraps up the lesson on radical functions, how to graph a radical function, how to tell the shift and the stretch of a radical function. If you have any questions for me, feel free to post them in the comments below, or get a hold of me by email and ask me, or when we get together on our days that we communicate and ask questions, feel free to ask me then. But I hope you're having a great day, and I really hope that we can get back to normalcy in the near future. I'll talk to you later.